Number 93 is a will a precipitate form question with a little twist. So we start with 0.1 liters of 0.2 molar potassium oxalate, which will break up into 2 potassium ions plus 1 oxalate ion, and 0.15 liters of 0.25 molar barium bromide, which will break up into 1 barium and 2 bromide ions. The question asks you to determine the final concentrations of all 4 of these ions. Now, 2 of them are going to be spectator ions, so they'll be easy to determine the final concentration of. Potassium is a group 1, and they are all highly soluble, so that's why we can tell that it will break apart from the oxalate. But it will also not form any precipitate, so it's not going to form a precipitate with the bromide, which leaves us with just the barium and the oxalate to form a precipitate. So we do the same approach that we did in will a precipitate form, in that we have to find the concentration when combined of each of these ions. And the concentration of potassium is going to equal the volume, 0.1 liter, times the concentration, 0.2 molar, divided by the final or the total volume, which is 0.250 liters. Because I can tell for every one of these that breaks up I get 2 potassiums, I will multiply that whole thing by 2 to get the concentration of potassium ions. And I get 0.16 molar. Staying with the same system, for the oxalate ion, I can do the same process again, putting in the concentrations. I would not multiply it by 2 because I only get 1 for 1, but I can also take a little shortcut. Every 2 potassiums has 1 oxalate. So I can simply say that this is going to be the concentration of potassium ions divided by 2. .08 molar. For barium, that's going to equal its volume, 0.15 liters, times its concentration, 0.250 molar, divided by the total volume, 0.250 liters. So for barium, initially it is 0.15 molar. And for bromine, again, I can go through the same process. I can put in the volume, concentration, and the new volume, but for bromine it's twice as much, so I would have to put a 2 outside like this. Or I can just take advantage of the relationship that says whatever my barium concentration is, if I multiply it by 2, that's going to be my bromide concentration, 1 to 2. Now at this point, we are done with the ones which are spectator ions. So we are done with potassium. Its final concentration will be 0.16, and we are done with bromide. Its final concentration will be 0.30. It's these two here that will form a precipitate. So if we check that out, we have barium oxalate, which would break up like that, have a KSP equal to the concentration of barium, times the concentration of oxalate, and substituting our numbers in to this expression, but since I know it's not at equilibrium, I use Q. That would just give me 0.08 times 0.15, which equals 1.2 times 10 to the minus 2. Since the KSP for barium oxalate is 1.6 times 10 to the minus 6, I looked it up in the back of the book. 1.6 times 10 to the minus 6, Q is greater than K, so a precipitate forms. Now the question is, what are the final concentrations? So this is that situation where I happen to have a great excess of the oxalate ions. So if they were dilute and about equal, one of these would attach to one of these and form the solid. But what I have is actually almost two of these for every one. I have an excess of the oxalate ion. So that means, oh wait, I just realized I'm calling these backwards. This is actually the barium and this is the oxalate. It makes no difference because we're just multiplying and there's no powers. But to say it right, I have a huge excess of the barium ions. And there are so many, there's almost two for every one, that they can force, that's Le Chatelier's principle, force this backwards and reduce these to virtually zero. All right. We can calculate it and see that it's not actually zero, but it would be times 10 to the minus 7. So within the range of our significant digits, it's pretty much the same as 0. So my concentration of oxalate is going to be about 0. And for every oxalate that I remove, I also have to remove a barium, so my concentration of barium will be 0.07 molar. We can only do this when we have an excess of one of the ions. If they were close together and still caused a precipitate, we would not be able to be certain that they would push the precipitate all the way to the left and that we would be able to reduce one to about 0 and the other one would be what's left over.